So there's not much left of the class. That's maybe a good thing. We have a few more hypothesis testing situations to deal with. They'll both have to do with the t-statistic. Today could be called the matched pairs day. I'll write it here. I'm supposed to be writing stuff. Here we go. So we might call this matched pairs. So more or less matched pairs has to do with collecting observations in pairs where the pairs are not, the values aren't independent. Somehow they're related to each other. Sometimes what you'll do is you'll take the subjects and you'll align them based on some explanatory variable so that they're similar with that possible explanatory variable. Then you apply a treatment. So you might be wanting to, we could, wondering which kind of weight treatment procedure might be the best, whether going to the gym or using Nutrisystem is better. And you might rank people by how overweight they are. I'll have someone, I'm in class, sorry. Yes. Her Zoom's not working. She's in trouble and I can't help her because I'm with you guys. My camera wasn't working when I got here. I had to restart everything. I don't know what happened. Oh, I was saying that you might have, you might wonder whether the Nutrisystem or going to the gym is better. You might have 20 people that are overweight to work with, and you might pair them up by how overweight they are. And then you would randomly assign them either Nutrisystem or going to the gym as a treatment, and you see how much weight they lost, and you might get something out of that. And that would be a matched pairs design where you match people up according to some explanatory variable. Here you think how much overweight you are might impact how much weight you can lose. Here I've got I'm wondering about blood treatment, blood pressure treatment. And so we take subjects, we measure their blood pressure beforehand and then after the medication, and we see what the decrease is. So the amount of decrease could be influenced by, well, the amount of decrease is influenced by how much the blood pressure was above to begin with. We don't want to just measure the after amount because people with high blood pressure probably have high blood pressure after treatment. We're wondering how much can you reduce blood pressure using medication. And so it doesn't make sense to try to treat these values as independent. This number impacts that number. So whenever that happens, you have a situation which you might call a matched pairs situation, and you treat it as a matched pairs experiment where you take the two values and you consider the difference as the variable of interest. Okay, so that's all fine and dandy. I'll show you a quick way to get this to happen in a minute, but right now we're just going to do the calculations. So it says, is there reason to doubt a claim that the treatment provides an average decrease of around 20 points? So if the mean here is less than 20, is it enough less than 20 that we think it's not just random variation, it's just the treatment doesn't quite give 20 points worth of relief? So we'll see. So we're just going to do a t-test on this. So how would that look? The t would look like, oh, t looks like this, x bar minus mu s over root n, like that. We're going to use these as our values. Here are my observations. Are the differences. So we don't even worry about these numbers. Once we've computed the decrease, we're going to use those as our observations. So I'm going to have to compute the mean. The mu I'm worrying about is this 20. And the standard deviation, I'm going to take the standard deviation of that. So sometimes I'll write it like this. The mean of the differences and the standard deviation of the differences over root n. But really it's just your old-fashioned t-statistic. And so we'll come in here and try to make this happen. So I'll go in, enter the values. Oh, I could enter the actual values. So I'm just going to enter the differences. Okay. So I'll double check these. 18, 15, 14, 8, 17, 15, 7, 20, 24, 30. Okay. And then I'm going to go to stat, calc, one variable statistics, and I want to use list one. That's where that was. And come down here. So we get X bar is 19.2. We get S is 5.308 something like that. And N is 10. We knew that. There's 10 values up there. And the mu we're going to use here is going to be 20. We see X bar is less than 20, not a lot. Is that far enough that it makes it look like the treatment doesn't quite do 20 points? Maybe it does more like 19 points. Let's find out. So go ahead and compute that. Oh, I'm going to compute it. Here it comes. Clear that. So I'm going to compute this t here. Parentheses 19.2. Can't see what I'm doing. There we go. 19.2 minus 20 divided by, and we've got the standard deviation, 5.308 divided by the square root of 10. Oops. Okay, so that's going to give us t, I'm thinking. See what it comes out to be. Minus 0.4766. Now, I've been computing these things for a while, and we know the numbers we're looking for are something like 2 if we want to reject the null hypothesis. So minus 0.4, they have to be like minus 2, something like that for it to work. Well, if we want to reject the null hypothesis. So we'll take a look. I have tables over here. Let's see. I found these tables in the back of the book that are on this sturdy, almost cardboard here. Kind of cool. Oh, I don't want that one. I want the T, the baby T. Where is it? They don't want to give it to me. There's a lot of pages here. It has everything except what I need. That's funny. Okay, toss that one. I want the real T, which looks like this. Oh, this will work. Okay. I think we're all right. Where is it? There we go. We do have it. Okay, so there we go. So over here, I've got degrees of freedom, which is one less than the sample size. Sample size is 10. So I'm here. Maybe I have this where I can draw on it. Let me see. I do. This is even better. Well, I got standard normal I can draw on. I don't have T. Is that right? Yeah. No problem. I'll just draw on this one. Okay. I have trouble holding this. There we go. Okay. So we're going to go here. Degrees of freedom is 9. And the value I got was 0.476. We discard the minus sign for looking up tail probabilities. So we're here. I'm looking for 0.47. It's not here any place. So as we move this way, the area in the tail grows. Here's the area in the tail here. So all we know is the tail probability is bigger than 0.25. Okay, I'll write that here. The left tail probability is greater than a 0.25. That's the last number they show here. Okay, and that's the p-value. And so we're not going to reject the null hypothesis. We might wonder how big a number would we need, say at the 0.05 level, a one-tailed test. We would need 1.833 to reject the null hypothesis. Would have needed minus 1.833 for t to reject HO. So we're not far enough out in the tail to do it. And so let's see what it says. We have to write some stuff up on the next page, see what it says here. It says, okay. So we put all that stuff in. We got t is minus 0.4766. We say the p-value exceeds 0.25, not considered statistically significant. We need something more like -2. State the results in context. If the long-term mean was 20, values such as those observed can easily happen. There is no reason to doubt mu equals 20. So the p-value sort of gives you an idea of how likely it is to see values such as those observed. It's bigger than a quarter. So we see that kind of a deviation from 20. The x-bar was 19.2 pretty easily when the mean was 20. And so we can't see any reason to think the mean is less than 20. And let's see.